so early in the morning just to listen to me. And it is indeed a great pleasure to be back here in Florence and at the GGI. I've been here a few times before, but it has been a while. So I've been charged with the task of giving you an introduction to ADS-CFT holography, and that I will do. I will start out at a very simple level. Too simple in a way, but still I need it in order to set the notation and the terminology for what I will do later on. And we're coming up to 20 years of ADS-CFT pretty soon, so it's no longer a really new subject. Well, maybe to me it still seems new, but I remember when I was in your chair as a student, something 20 years old was already ancient. Right? Already well worn and some part of history, in fact. And indeed, it has probably gone there in some sense. But it is a good time to look back and focus on the big ideas. And that's because this field, of course, could use some big ideas. And the big ideas are not up to me anymore. They're up to you. So that's where I hope we're going with this. As I go along, please feel free to ask questions. In fact, feel obliged to ask questions. Maybe if you don't ask me any questions, I will ask you some questions. In order to keep the discussion alive. All right, so let me outline what I want to talk about. So I'm assuming 6 lectures, so I'm writing here 6 topics. I don't know about the speed at which I will go through these, so I can't promise I'll get to all 6. Sometimes things go slower than one anticipates, and seldom does it go faster. So I'd like to talk today about some topics just in gauge field theory. So I am by education someone who works on quantum field theory, not string theory. So I will approach this probably from a different point of view of your other lessons. You've had some very high-powered lessons on string theory, one last week and one ongoing this week. This will be a slightly different approach, assuming that you don't really need an introduction to string theory and actually using very few of very little of the technology of string theory. So I'm going to talk about gauge theory, then I'm going to talk about the original derivation, the original argument of Maldacena, which sits there today as really the only real derivation of the subject, and is not really a derivation, which leaves the whole thing a conjecture, but still it's interesting to review it. I'm going to talk about holographic Wilson loops. Not because they're the only holographic thing, of course, but because the logic fits nicely with what I will say up to there. Then I'll talk about holography in more detail. Correlation functions, the full ADS-CFT dictionary and all that. And then I will discuss a direction towards some applications. One of them being my favorite way to go to applications, called probe brains. And then at the end, if there's time, I would like to discuss the most concrete application I know of, where one actually computes something. And you'll see what the something is. It's not really a number that I can take to the condensed matter physics lab and tell the experimentalist to look for. In fact, none of this science is quite at that point, but it is at least something qualitative and somewhat quantitative about a strongly coupled system. And this is something in condensed matter called quantum Hall ferromagnetism. Okay, so that's 6 subjects for 6 lectures. And I will do my best to get there. Okay, so with that said, let me begin with some easy things. An introduction, mainly to set the notation of what I mean by gauge field theory and gauge fields from the beginning. Now, I should say that string theory has been around for a while as a speculative theory to describe Planck scale physics. As far as I know, it's still on the table, hasn't been ruled out. The main criticism of it is that it can't be ruled out because experiments will never get there. Maybe it can and maybe it can't. It doesn't really matter to us here because we're not using it for that. We're using string theory to describe gauge fields. And as such, since gauge fields will always be with us, they seem to be a correct description of fundamental physics as far as we know it today, up to the experimental, the scales that are accessible to experiment right now. So gauge fields are certainly with us. And from the point of view of these lectures, gauge fields are also string theories. So in this sense, string theories will also always be with us. So this is not something that will go away in a century. Even it will still be there. Something like Maxwell electrodynamics is still with us and probably always will be, even if it's moved over to the engineering school from the physics school. It could be that in 100 years this stuff has also moved over to the engineering side of the university. And so it's useful to begin with gauge theory. So I'm going to work with Lorentz invariant things. I'm going to use the East Coast convention for the metric of 4-dimensional space-time and space-times of other dimensions. That's the one with signature -1, 1, 1, 1. To me, a gauge field starts with the 4 vector, or the vector connection field. And we'll consider gauge theories, which are based on gauge groups, which are some Lie group. So this is typically takes values in the fundamental representation. Of the Li algebra. And this Li algebra should be associated with the Lie group, which we call the gauge group. And for ADS CFT, the most important one, in fact, the only one that I'll really have anything to say about, is the Li algebra SUN. Or UN. And in fact, since I'll be talking about large n, there isn't much difference between the two. There are small differences in the 1 over n expansion. And when it matters, the easy one is un. That's the one that has a nice, easy 1 over n expansion that we will learn about. SUN is a little bit more complicated. In fact, I would be challenged to put in the corrections from SUN. I know it is possible, but it gets a little bit technical. So we will typically focus on UN. So in a UN gauge theory, the gauge field is an n by n Hermitian matrix. Pardon? It transforms in the adjoint, but it takes values in the fundamental. Right? So for SUN in particular, UN also, the fundamental representation is n by n, and that's what it is. So it's a matrix, n by n matrix. If it were an adjoint, it would be a much bigger matrix, but it transforms in the adjoint, it's true. I guess this should be capital. So it's an n by n Hermitian matrix, and that's when it's in UN. When it's in SUN, it's a traceless Hermitian matrix. Not much difference, but enough difference to mess things up. So we could stay with UN. The actual gauge group of the field theories I will be talking about could be either UN or SUN, and maybe I'll remember to discuss that when the time comes. Okay, so what is it used for? Well, a gauge field is a connection field, so it has something to do with coordinate transformations. These coordinate transformations are not the coordinate transformations of geometry or of general relativity, of actually changing the coordinates on the space in which you're doing physics. They're coordinate systems which are quantum mechanical of nature and have to do with changes of the phase of the wave function. So you think of the phase as a wave function as a coordinate on a certain space, right? In a sense, you put a wave function everywhere on our space, and then the wave function has a phase, so you add another dimension, and then changes of that phase are the coordinate transformation. An n by n matrix we would use on n component wave function. So if you have a quark wave function, that has n components, a change of phase, so to speak, is the multiplication of the wave function by a matrix which depends on location, the point at which you're talking about the wave function, and is in the group where a mu, which is associated with the Li algebra where a mu lives. So let's call it UN for now. So G of x is a UN matrix. So does that mean? Well, that just means it's a unitary matrix. In that its Hermitian conjugate is its inverse. And we think of this as a coordinate transformation of a sort. And then when you can do coordinate transformations that are local, of course you should do a little bit of work to define what you mean by derivatives, to do calculus in such a system. And that's where the gauge field comes in. It's used to make a covariant derivative. Which as usual is the ordinary derivative and n plus something with the connection field. And then how the connection transforms when you do the coordinate transformation is dictated by requiring that the covariant derivative transforms in the same way that the wave function did. And of course, from this you can figure out precisely how it transforms. And it looks something like that. Okay, so you have a covariant derivative. Along with the covariant derivative, of course, comes all of the other things of geometry, like a curvature, and then some dynamics, something which determines what this geometry is. In other words, equations of motion of some sort. So the covariant derivative has a curvature which also is an n by n Hermitian matrix. And as usual, you can think of it as a commutator of covariant derivatives. And then a little more explicitly, it looks like this. And of course, the curvature is not invariant under coordinate transformations, just like it wouldn't be in geometry. It changes when you change the coordinate system in a specific way, but it transforms in a decent way, just like the curvature tensor in geometry transforms like a real tensor. This one transforms like this. Okay, so this is the structure of what a gauge field, a connection and its curvature should be. Then to make a dynamical theory, one needs to postulate some dynamics. And that part, of course, is physics, it's modeling. But a very reasonable model would be one that wants to make this curvature small, or in the absence of sources, 0. And so we could write a Lagrangian whose saddle points, or whose classical extrema, when you make it into an action, of course, and look for classical extrema, would have the curvature equal to 0 for now. And such a Lagrangian might look something like this. So F mu nu are Hermitian matrices. So take a product of two of them. The upper and lower Lorentz indices are the usual stuff, raised and lowered with the Minkowski space metric. So take a product of two of them and take a trace. That's a nice quadratic form that you expect is minimized when f is equal to 0. Of course, this is not a positive quadratic form because of Minkowski space, but that's the usual thing. In fact, it's a straightforward and rather obvious generalization of the case when f is 1 by 1, which is Maxwellian electrodynamics. So here it's an n by n matrix. One thing which I have not discussed at all in all of this is what you would call a coupling constant. So let me talk about that for a moment, because that's something important to get the convention straight to use later on. I use a convention for the coupling constant that's used in almost all the ADS CFT literature. but unfortunately didn't make it into the probably the best textbook on the subject, the one by Johanna Erdmanger and collaborators. She uses some convention which differs by a factor of 2, which can lead to endless confusion. But let me tell you what mine and other people's version of the coupling constant is. It simply can be introduced in the following way. So we'll put in a coupling constant. So this coupling constant is something which governs the nonlinearities of the field theory. I see I've already made a misprint here, actually. So I'm very sorry. I want a half in front of here. For various reasons. For a reason which I'll explain to you in a moment, just to be clear. I want a half in front of there. You can put a coupling constant in one of 2 places. You can put it in front of the Lagrangian density. Or, in all of these expressions over here, you could put it in front of a mu of x. That is in front of the a mu of x that appears in the covariant derivative. Maybe I should write that more clearly. So when you have a covariant derivative, d mu minus I a mu, you change that to d mu minus I times a coupling constant, which I'll call the Yang-Mills coupling constant, g sub Yang-Mills times a mu. Now, in this simple place, these 2 ways of doing things are actually the same. You can get from one to the other by scaling the gauge field, the vector connection, by probably 1 over g Yang-Mills. If you do it this way and write down all of this, the g appears inside of f somewhere. You can get back to this form by redefining a as a over g, and the coupling constant comes in front. That's sort of important in perturbative quantum field theory, because that tells you that this coupling constant really does count the number of loops in Feynman diagrams. Right, so the loop expansion is weighted by this g Yang-Mills coupling constant properly as you expand. Now, the loop expansion will not be of huge interest to us. We're interested in different kinds of expansions, and this coupling constant will play an important role there too. Why do I put 1/2? Okay, very good. This is a good question. Some of my collaborators who were from Germany at one time, when we were working on things like this, said there are 2 kinds of physicists who study this subject. 2 kinds, and these 2 kinds can't talk to each other. That's because some of them treat f mu as a matrix and a as a matrix, as I have described to you. And some of them expand these matrices in a basis of the Li algebra, and then they take f mu and a mu in the Li algebra components. Okay, so there are these 2 camps. I guess you can see which camp I am in, although I like to think of myself as one of the people who can talk to both sides. I do prefer, for the purposes of what I do here, to do things this way. You go to the other one by choosing some generators of the Li algebra. So for SUN, there are n squared such matrices. And you do this. And conventional particle physicists love to do this. And they will usually write Yang-Mills theory in terms of these n squared, or n squared minus 1 in the case of SUN. So n squared in the case of un, like I've written here, in terms of these components. And then the traditional normalization of the basis vectors of the Li algebra is this. So there are a bunch of Hermitian matrices which are normalized, which are first of all orthogonal if you use the trace as a norm, and then secondly normalized so that each of them has norm a half and they're orthogonal to each other. And then if you look at the Lagrangian, with this normalization, it has minus a quarter. Like so. Okay, so it has a convention where this is minus a quarter, like in Maxwell electrodynamics for these components. And then going back through this, you can see the matrices to match this normalization. There's a half over here. So that's why the half. And if you look through the big old review papers of ADS-CFT, dating back to the one called Magoo by Maldacena and a bunch of other co-authors, this is the convention that's used everywhere. Okay. Okay, so this is what the gauge connection and the curvature is. Now let's use it for something. Well, once you have a connection in geometry, the thing you like to do is talk about parallel transport. That is a convention for transporting the wave functions around. So our wave functions are n-component things. This convention should be compatible with the geometry. Maybe transporting is not quite the right way to say it. Probably it's more like comparing wave functions at different points. So you want to compare a wave function at point x with one at point y. If you're allowed to do gauge transformations, that would seem like a difficult thing to do. You have to decide on, when you compare them, what matrix, g of x, to multiply it by before you make the comparison. So parallel transport is a canonical way of doing that. And the real purpose of having a connection is to give you this canonical way. So the data for doing this comparison is stored in the connection. So if you want to compare this at phi of y, the correct thing to do is not just to compare phi of x and phi of y. The thing to do is that the geometry tells you is that you should compare it instead with some unitary matrix that you multiply on phi of y. And that unitary matrix is made out of the connection. And what it is something which actually depends on a path that you choose between the two. So if I could draw a picture here, here's phi of x, or here's the point x, phi of x is there, phi of y lives at the point y. There's some path between the two that's oriented from y to x, and let me call the path c. So this path labels the unitary matrix that does the so-called parallel transport. And what this is a path-ordered exponential of I times the line integral along the curve of the connection field. So just let me write that, assuming I have a parameterization of the curve. The parameter tau. So it should look something like this, where in some coordinate system, the progress along the curve is recorded by this curve parameter tau, and the position of the curve for a given tau is given by this trajectory function x mu of tau. Okay? So that's what I mean by this thing. Then you take its derivative to get the tangent to the curve, contract that with the connection, and that's the thing that you path order and line integrate to get the parallel transporter. Of course, under gauge transformations, this matrix that implements so-called parallel transport also transforms covariantly. It's not an operator yet. No, P is path ordering. Path ordering, right. So path ordering is something you do in time-dependent perturbation theory, where you study quantum mechanics. So let me just define what it is. Okay, let me come back to some space here and define what it means. Since you asked the question, that's good. So one can define this, and often you will often do, in fact, probably where we define it, we will do it that way too, by Taylor expanding the exponent, first of all, in the exponential. And then, in the terms in the Taylor expansion, you get things like this, the product of n of these. These are all identical integrals, but let me put the integration variables different in them anyway, just so the thing makes sense. This is, of course, the tangent vector. Okay, so it looks something like this, a product of these things. In the nth term in the Taylor expansion, maybe there should be I to the n over n factorial in front, and the summation. And this is what u was. Okay, and then what path ordering does is simply orders this product of matrices. So these are not operators. So normal ordering is not the way to think about it yet. These are not quantum mechanical operators, and in fact practically will never be for us. Right? They're just a bunch of matrices, but of course generic matrices don't commute with each other, so you have to say something about the ordering. And what the path ordering does is orders this product of A's so that the earliest ones on the path, the ones closest to the beginning point of the path, come to the right of those that are closer to the end point of the path. So this is an increasing occurrence of the argument tau on the path itself. So that's what the path ordering means. And this path order thing is actually a solution of the following equation. You might wonder where one gets this. All right, I just dragged it up. But it is a solution of some equation. It's a solution of an equation that you get if you take the covariant derivative, project it in the direction of the path at the endpoint of the path, you require that this matrix obey an equation like this. Actually, it's not quite this, sorry. It's if you parameterize the endpoint of the path by a final point here, yeah, okay, that's already in the covariant derivative. Yeah, that's fine. So you take the covariant derivative, this depends on x. It's a path-dependent thing, so this covariant derivative doesn't make a lot of sense unless you specify a direction along which you're doing the derivative. So that specification is done here, contracting with the tangent vector. And then you require that this is as close as you can make it is equal to a constant. In other words, a covariant constant along that direction. And that's the equation that this thing should satisfy. And then hopefully the factors of I and minus sign here that were in my notes are correct, so it actually does satisfy that equation. The motivation for this, well, remember I was saying about comparing wave functions at different points. Well, you want to compare them at different points by translating them in a way that's closest as possible to them being constant. Right? If we measure two numbers, u and I, and we don't have this geometry, we would just compare them and we would say that whatever quantity we measured is a constant if we got the same measurement. Here, if you're talking about this wave function, u and I have different values of this wave function. How do we know if they're the same or not? Well, the system in which we, the geometrical setup in which we compare them is one where when I transport mine over to you to compare it to yours, I keep it as constant as possible. Right? So when there's a connection in the geometry, as constant as possible means the transporter obeys this equation. Okay. Then the transporter under a gauge transformation is actually constructed so it gauge transforms that way. So that it gauge transforms by the function g of x appropriate to each end point. It is an n by n matrix. In fact, it's an n by n unitary matrix. That might not be so obvious from the construction, but it is. It's an n by n unitary matrix, and then it transforms like this, which keeps it unitary. But indeed makes it transform. This means that, well, not all of its properties are invariant under coordinate transformations in our geometry. Right? You choose a different coordinate system, that's like multiplying everything by this g of x, changing coordinates. So what is invariant? What are the things that actually matter in here? Well, they're the things that are that somehow one could pick out of here. It's not that simple a question for a general parallel transporter like this. One way one can simplify the question is by transporting in a loop. Okay, so this is for transport where you begin at point x and come back to point x. So let me draw the picture up here. Here's x. You go along some curve and you come back here. So this curve is c. This transforms in a nicer way. Well, slightly nicer in that the g of x and g minus 1 of x are at the same point. Okay, so this is still not invariant under coordinate transformations, but it transforms by conjugation, and that means you can pick out of it things that are invariant, right? Those attributes of it that are unchanged by conjugation. And what are those things that are unchanged by conjugation called? Maybe the eigenvalues? Right, it's a unitary matrix that should have a bunch of eigenvalues. Eigenvalues are unimodular complex numbers, phases, but it should have a bunch of them. So the eigenvalues are actually invariant under this conservation. And so it does have a bunch of data that is coordinate invariant. They're the eigenvalues of this thing. And generally, they could all be of interest to us for a given Yang-Mills field. We could go and devise some mathematics to extract the eigenvalues of parallel transport for different curves that come back to the same point. And those should contain all the data that are in our Yang-Mills field, and it's all the important data because that's really coordinate invariant stuff. And normally we don't bother with all of it simply because that's a difficult problem. And we'll jump to quantum field theory where these things are operators, and then it becomes even more difficult problem. But one thing that we do like to extract is, say, the average of the eigenvalues. So what's the average of the eigenvalues? Well, there are n eigenvalues because it's an n by n matrix. The average of the eigenvalues can be gotten just by taking their sum and dividing by their number. The sum of the eigenvalues of a matrix is actually given by its trace. So this is the sum of the eigenvalues. Well, actually the average of the eigenvalues. And this is important enough that we'll give it its own name. This is something which I will call the Wilson loop, which is labeled by the curve that you're using. And this is something which we'll promote to quantum field theory and talk about there. So this average of the eigenvalues is a kind of a diagnostic for the nature of the connection. You could see one could be more powerful and ask harder questions, but this one will turn out to be hard enough. And it will also turn out to be good enough to tell us in the quantum theory something about the state of the quantum system we'll be describing. Okay, so it's already good enough, and this is something which we'll carry along with us and compute, talk about computing from time to time. And here it's written maybe rather obscurely, the Wilson loop is a function of some curve, or the operator itself I'll take as being defined by. I might drop the 1 over n, simply because, well, if I know the average, I also know n times the average, and so that sort of thing is just a matter of convention. So I'll drop the 1 over n and take a trace of the path-ordered exponential of now the integral around a closed curve of the exponential of this integral of the tangential component of the gauge field. Now along a closed curve, and one of the beautiful things about this thing is it actually doesn't matter where the beginning and end point of the curve was, as long as it's on the curve. So we should now picture that curve over there, which I'll try to reproduce here. It had a beginning and end point x, but once you construct this loop, it doesn't really matter which beginning and end point you called x. It closes up. It's invariant under our coordinate transformation, or perhaps could be, we should start calling it a gauge transformation. And it depends only on the curve that you have, and it carries some geometrical information. So this will be an important player when we go to talk about quantized gauge theory. We will discuss it there. In fact, I can make the jump to quantized gauge theory rather easily. So let me forget about all the technicalities in quantized gauge field theory, of which there are many. If you sat through a field theory course, you already know about that. It takes about half of a semester to actually go through all the details. Let me not do that, of course, but just jump to a definition of what I mean by the Wilson loop in a quantized gauge theory. So there, of course, we should talk about its expectation value. In the gauge theory, this is a ground state or vacuum state expectation value normally. And what it is in my dynamical theory of gauge fields, and perhaps other things, which I won't talk about right now for simplicity. I take an exponential of the action, which is gotten by doing a volume integral. Let's say we're in 4 dimensions. Of exponential of the action, and then I put this classical operator. Classical operator, that's a contradiction. This classical quantity made out of the classical fields over which I'm integrating here inside the functional integral method. And you can think of this as just a definition. Of what I mean by this expectation value. Here I've normalized it so that if W happened to be 1, the expectation value would be 1. A nice safe way to normalize it is to just divide by this functional integral. And so this is some sort of averaging over function space of the classical operator as a function, functional of the functions that you're averaging over. Yes?
What about the hosts? Don't we have to introduce the FDF-Popov determinant when we introduce the integrator of the gauge?
We absolutely do. So we have to do that. We might have to put some quarks too, okay? But ghosts we do, absolutely. So we will do that in a few minutes.
Okay.
So you can think of this as a schematic. Actually, since this is gauge invariant, this side will not depend on how you fix the gauge. So that's sort of one reason why I don't do it here, right? Faddeev-Popov ghosts, in a sense, imply a relativistic gauge fixing. So I don't do that here. But to do some calculation beyond this point, for sure you do. So when I start talking about perturbation theory, there isn't a choice but to fix the gauge. So that's a good point. And of course, that's done upstairs and downstairs in the usual way. So there's a whole bunch of technology there, which we will skip over. Okay, so why is this quantity interesting? Well, in quantized gauge field theories, this has been something of extreme interest already. It's a diagnostic of how the gauge theory works. It's called the Wilson loop after Wilson, who was the one, I'm not sure he's the one who introduced it, but for sure as a diagnostic, he's the one who suggested using it this way. As a rough diagnostic, works something like as follows. So here the curve in the Wilson loop is some specific curve. If the behavior is of one of two possible types, so you take a large and fairly symmetrical curve, and you ask, how does this expectation value that you compute this way somehow behave as you change the size of the curve? So take a nice big curve that's smooth, circle, square, whatever you like, expand it and contract it. How does WC change? If it changes like the exponential of the area, that's said to tell you something about the nature of the gauge theory. In fact, this is a signal of confinement. This area scaling law. So back in the early days of the use of Yang-Mills theory for the strong interactions, which are supposed to be confining, this was taken as a diagnostic of the fact that Yang-Mills theory as used for the strong interactions based on SU3 is confining. And particularly in solving this theory numerically, this was one of the things to look for. Right? Does it scale like a area or the perimeter? Now, I guess there are other possible scaling laws, but there isn't that much that's really compatible with geometry if this is a big and nice smooth curve. Perimeter means it's deconfined. And in fact, you can see that it implies, in a sense, it implies that the gauge field, the interactions, mediate a Coulomb interaction between quarks, Coulomb-like, like electrodynamics. So it's deconfined, and in these two scenarios, in the confined one, if it scales like the area up here, there needs to be a constant with dimensions out here. And I haven't talked much about dimensions, but in 4 dimensions, my Yang-Mills theory actually, before you quantize at the classical level, has no dimensionful parameters in it at all. So there's nothing with the scale of dimensions in the theory itself that could appear here. So dimensions have to come from somewhere. They have to be generated dynamically. Well, there is actually some kinematical stuff having to do with renormalization and running couplings. So there are hidden dimensions when you quantize, dimensionful constants. But in any case, it has to somehow decide to put a dimensionful constant here, and what that constant is, some parameter of the phase of the theory. So you could see that this theory is going to have to be highly nonlinear in order to generate such a constant. Interactions have to be strong, and so on, but it should come there, and it should, in a sense, govern this area law. And this thing is called the string tension. In the perimeter case, there's also a dimensionful constant here. And typically this constant is infinite. And what it is, what you can think of it as, is the mass renormalization of a heavy quark that this Wilson loop calculates the holonomy of. So there's some mass renormalization, some infinite shift here, and then a perimeter law, which just tells you how the quark interacts with itself. And the perimeter law means that in some sense the interaction is short-ranged enough that as you drag the quark along, it only interacts with itself at locations shortly before where it is and shortly after as it's moving along this trajectory. This one means that it interacts with itself everywhere, that it pulls on itself at the other side of the trajectory, and so on. And so that's the difference between confinement and deconfinement. So these differences were very important early on in the study of Yang-Mills theory. That's because Yang-Mills theory, well, it was always used for the electroweak part of the standard model, where it's actually nice and weakly coupled and one can do things. But the great mystery was it's also should, an SU3 Yang-Mills theory called QCD should describe the strong interactions. And the strong interactions, when it describes them, the color degrees of freedom, the things that the gauge field couples to, are actually supposed to be confined. So it is in a confining phase. It's a strongly coupled problem from the beginning. So analyzing strong interactions using QCD is strongly coupled. The analysis is strongly coupled, non-perturbative, and in a lot of ways an open problem to this very day. Right? QCD works. It's been adopted as a model for these interactions because in some domain it works. Because of asymptotic freedom, it works at high energies or here for very small trajectories. But to actually derive this from QCD is still an open problem to this day. I should say that it has been done numerically. Right, so if you're faced with a terrible integral like this, you being from a very modern generation might immediately go to the computer, right, find a way to define those integrals on the computer and just go to work, crank out a solution. And in fact, that's been done. There's been many beautiful computer experiments calculating this Wilson loop, which I will say a few things about in a moment. And this picture has been to some extent confirmed that way. But analytic approaches are still lacking. Okay. Let's see.
Sorry? What do you think about design theory in which it's independent of the path, and non-trivial, in which takes just a constant?
That's independent of the path, completely independent of it? So you mean this quantity is independent of C? Well, that would be a theory with not much structure. Well, topological field theories are like that. It might say depend on topological data. So not on the details of the path, but where the path goes in some sense. Right, so that is possible. Chern-Simons theory, for example, in 2+1 dimensions. If the underlying manifold has some topology, these things would depend just on topological data. So it is possible, but for generic gauge theories, it's not like that. It will depend on the details of where it goes. Okay, let me keep this. Well, we're theorists here. We're pure theorists. Let's pretend we don't know how to use a computer. I don't even have to pretend. So how would we set out to actually do a calculation? We want to do something quantitative. It will turn out that calculating this thing directly is difficult. Well, it depends a bit on the dimensions. Actually, in 1+1 dimensions, this is an exactly solvable problem. It depends a bit on the geometry of the underlying space. But if it's just, if the one space dimension is just the open infinite line, and the time dimension is also the open infinite line, so space-time is basically open and infinite, this is a solvable problem there, and one can actually do the calculation. And the Wilson loop does exhibit an area law in space-time, particular if you go to Euclidean space. So two-dimensional Euclidean space is just the plane. There the Wilson loop does have an area law in 1+1 dimensions. In fact, the coupling constant there has dimensions. Yang-Mills squared has the dimensions of a string tension, and it turns out to be the thing that appears there with the area law. Already in 2 dimensions, 2+1 dimensions, this is not a solvable problem. 3+1, where we would like to solve it, because we model certain things with this theory. It also is not exactly solvable. And in fact, the only real analytic tool we have is perturbation theory. Of one kind or another. So what does perturbation theory do? Well, we know how to do Gaussian functional integrals. So you can look up in a textbook how to do it. It won't be very important for us for a while, so I won't give you any details, but we know how to do Gaussian functional integrals. This is not a Gaussian functional integral. F mu nu has some leading terms that are quadratic. If you truncated those leading terms, it would be Gaussian, and you'd have some hope of doing this. but then it has other non-quadratic terms in it that make the integral non-Gaussian. So what perturbation theory does is basically Taylor expands in the non-quadratic pieces of the action so that they come downstairs into the integrand of the functional integral down here, and then probably Taylor expands in the phase in the loop operator, and so you have a whole bunch of Gaussian integrals to do with stuff downstairs. It's known how to do those, and that's called perturbation theory. And the nice representation of those is called Feynman diagrams, and it's the usual diagrammatic perturbation theory, how you calculate things perturbatively. Yes? You want to have a break? Right now would be best. Okay, 5 or 10 minutes. I also feel like stopping, so I don't mind. Okay, so I had come down to discussing how to compute this thing. And really our only tool, our tool, is perturbation theory. And perturbation theory is not very good, particularly for a confining gauge theory, for many reasons. But for this Yang-Mills theory, there's actually a very simple reason that, of course, this is a quantum field theory computation. And so it has to be regulated and renormalized like any four-dimensional quantum field theory computation. And when you do that, the coupling constant we've been talking about, G Yang-Mills, gets a beta function. And that beta function makes it asymptotically free. So it turns into a running coupling constant, which depends on the scale, or a comparison of scales, the scale at which you're computing something, divided by a canonical scale, which looks something like this. It's 1 over 11/16 times a log of that ratio of scales. And this is a one-loop result, but that doesn't matter very much. What it tells you is that well, first of all, this is computed in a regime where the computation makes sense, where the coupling constant is small, and that turns out to be at a fairly high energy scale. So this ratio down here inside the log is bigger than 1, and the log of it is a positive number for that reason. If that energy scale gets very big, actually this effective coupling constant gets very small. That's called asymptotic freedom. That's, of course, a great result. Asymptotic freedom is one of the cornerstones of this science. Nobel Prize was given for the computation that found it, maybe more the interpretation of said computation, but seems to be a property of the strong interactions that this Yang-Mills theory is formulated to model. On the negative side, as you make k smaller approaching mu, this log approaches 0, this coupling constant gets very big. Of course, there, you're in a regime where the coupling constant is big, and the perturbation theory, the expansion in the coupling constant, which one used to make the calculation which found this in the first place, is not valid. Right? So it ruins perturbation theory when k squared gets small enough. And in fact, this should always happen according to this formula. K squared small is big distances. These big distances are exactly where we would want to do one of these computations to test the behavior of a big loop. So those computations in a quantum field theory with this running coupling constant cannot be done perturbatively for this reason. So this running coupling, well, it comes from renormalization, and it's a typical behavior of a renormalizable quantum field theory, that dimensionless constants in that theory become, in a sense, dependent on the scale, and this is one of the most famous examples. So at the same time that this is a beautiful result, it tells us that in much of the interesting regime, this is not going to be computable by perturbation theory. So what to do? Well, theoretical physicists are very creative and very clever people. And so over the time, there have been many ideas about what to do. Non-perturbative calculations, instantons, things like that. I think when I was a PhD student, the instanton stuff was the rage. Everybody was working on it. It turned out it didn't really work. It never became a quantitative tool. There was a nice idea that somehow there are semi-classical, classical configurations of a mu that are non-trivial and contribute to the integral, and you can integrate around them. But it never really worked in that it never really led to an answer. And quite a bit of energy was expended. And in some sense it didn't work. And there was another conjecture around, which actually comes from about the same time, and that's that perhaps there was another description of this dynamical theory, at least in the long distance limit, that there was a different way of labeling the degrees of freedom. And that way was to label them as a string theory. And this might be in the effective sense, in that it would describe that theory only at large distances. Or maybe in the exact sense, it would be an exact dual of that theory, some kind of transformation you could do to the variables to make it that way. And that would rewrite this problem of calculating the expectation value of the Wilson loop, something like this. As a sum over geometries, that is, some disk-like geometries. So I'll tell you a little more what they are, but they're disk-like objects, such that the boundary of the disk, that's the wrong thing for boundary, the boundary of the disk is equal to this curve C in the Wilson loop. There's some measure here which one really has no idea what it is. It depends on the two-dimensional object and perhaps on the topology of the disk, which we could call the Euler character. And then this string tension should make an appearance, this e to the minus sigma from the area, and it should multiply the area of this two-dimensional surface, like so. Before I fill in this part, let me draw a picture of this. So here's our curve for the Wilson loop. And this model is saying you should be able to calculate it as some sort of statistical sum over surfaces. These surfaces are surfaces whose boundary is this curve C. So something like this. Formulate a sum over all these surfaces. That's already a mathematical problem. Weight that sum somehow with some measure. And then the important thing inside this measure is e to the minus string tension times the area of these surfaces embedded in your four-dimensional space. Then these surfaces themselves could have some geometry. They could have holes and handles. So they could have some non-trivial Euler number. This measure could presumably depend on the Euler number, and you should sum over Euler numbers. And then typically you could weight that sum by something you might call a string coupling. So there are two important constants here. One is this thing that tells you how fast the sum falls off with more and more complex geometries or topologies of the surface. And then this tells you how it's kind of a Boltzmann weight. It falls off for very big surfaces. So the conjecture is maybe one could find some other variables in which this equals this. Well, that's really ambitious. Maybe, though, one could also find something for where this curve is really big, much bigger than the scale of the string tension. Maybe in that limit this equals this. In either case, actually, there wasn't much success in this business for a long time. Before I tell you where the success did occur, I should tell you some of the reasoning for even wanting to do this in the first place. Yes?
Do all asymptotically free theories show confinement?
That's a good question, because of course confinement, asymptotic freedom is something perturbative, right? You do a calculation, you find a beta function, and the theory is asymptotically free, which means your calculation was very good at high energies and not very good as you lower the energy. So to be completely honest, as you lower the energy, you have no idea where the theory goes, right? Confinement is a conjecture. However, it has fairly good numerical support. So there is some evidence that it's right, that's sort of beyond perturbation theory. But let's talk about evidence that somehow this theory could be rewritten as a string theory. So why would that ever be? Well, first of all, there is confinement. And the essential part of confinement is this string tension. Now, you might see that string tension, well, early on it was more or less seen in the spectrum of hadrons. Yes? It's continuous, in fact, it's more than continuous. So this sum you should think of as a representative, as not really a sum. Of course, it's not discrete. Right? For sure, it's not discrete. But I don't really know how to write it, so let me write it as a sum. Okay, you should imagine it as some kind of a almost a statistical model, summing over all possible surfaces. You have to do lots of work to define that sum. Right? Very smart people worked for many years to try and define this summation as an integral, of course. So let me leave it at that. Yes?
Would increasing the genus of the surface add to another curve? Change the value. Given speed of light, would that not take the genus of the surface?
No, it doesn't. Because you could have a surface that has, let me see. If you have a surface like this, it could have an object. Let's say it's a disk, it can have a handle on it like that, right? So in a sense, increasing chi means increasing the number of handles here. Actually, it's decreasing chi, because the Euler number is equal to 2 minus 2 times the number of handles. Okay, so one needs something to control this, otherwise the surface becomes really broken up. And you don't want it broken up, just thinking about what you want. You want something with a well-defined, fairly simple surface here, at least something that dominates this sum. And so you control it with this string coupling. And then the area law also tries to make the surface small. Of course, this doesn't really work. But let me first review why one might think it would work, what the dream was. And so the dream was that you have a theory where confinement and the emergence of a string tension for the Wilson loop would just come out semi-classically. Somehow the surfaces that dominate this sum would be ones that are fairly smooth, not that big, and then if you have a dominant surface, that would give you an area law, because this is the area of the disk of psi. Psi is not much different from the area inside the curve if this isn't too wildly fluctuating, and so you would get an area law out automatically. So that's one reason for thinking such thing might exist. So confinement, the string tension, area law, semi-classically. Another thing was that, well, this theory was used to describe the strong interactions, and in the physics of the strong interactions, the theory of mesons, baryons, and all of that, there are some features of the spectrum of a string theory. Some fairly good Regge trajectories of various kinds of mesons, which are really there. Now, they're not perfect by any means, right? This is real observational data, things that you see, but they're there and distinct enough, visible enough, that you might wonder, is there a string theory underlying the strong interactions? And in fact, that wonder predates the use of Yang-Mills theory to describe them. It comes from the 1960s, where stringy models, in a rather indirect sense, really were used to attempt to model them. Then, of course, there is numerics. Lattice gauge theory. Now, this is more recent. This isn't ancient, but I think I sat maybe in this very room in a nice conference of the GGI, where Mike Tepper from Oxford was telling us about his numerical results. And that was for a 2+1 dimensional Yang-Mills theory. But I remember that as being particularly impressive. It's a few years ago now, because what they could do is put a source, an anti-source, and actually measure the string tension numerically in Yang-Mills theory. And not only could they do that, but they could excite the string, had some way of exciting the string, and they could even see the higher levels of the excitations of the string, and match them to just the bosonic string in 2+1 dimensions. And I think they could match them up to level 7 or 8. It was really impressive. So there's some numerical evidence that Yang-Mills theory can be described by a string theory. It's more recent than the ancient stuff, but indeed it's there, and it's rather good. And then there's some other bits of evidence. For example, there's a so-called large N expansion. This is due to 't Hooft. Also a long time ago. But what he did is he took the perturbative expansion, this problem, and reorganized it into an expansion that looks something like this, controlled by something he'd identified as a string coupling constant. In fact, in that expansion, the string coupling constant was equal to 1 over n. Actually, the closed string coupling constant, well, equal to 1 over n, that normalization. And that was also very suggestive of some kind of stringy structure underlying Yang-Mills theory. Okay, so this was a long-time conjecture that many people worked on and studied. Numerics seem to back it up in some sense, but it never really found a quantitative model until ADS-CFT came along. And in ADS-CFT, there is at least one example where all of this stuff actually works. And strangely enough, in that example, it actually isn't even for a confining gauge theory. It's for a deconfined gauge theory, which doesn't have a string tension, but this kind of a mapping still works. So let me discuss it a little bit. So in ADS-CFT, what it works for is not exactly the Yang-Mills theory I've been formulating here. It's a Yang-Mills theory with additional stuff, additional fields. So I should write a ... after the integration variable. What the Yang-Mills theory is a maximally supersymmetric Yang-Mills theory. So one has to add the fields to complete the super multiplets. Maximally supersymmetric means there's a lot of them, scalar fields and spinor fields and so on. There's, of course, the other terms in the action. It is 4 space-time dimensional, defined on flat space. So for that Yang-Mills theory, one can also define a Wilson loop. One can come and give this argument. That Yang-Mills theory actually isn't confining. So that's the interesting thing. The one concrete example that's been found where all of this works somehow avoids part of the motivation for looking for such a thing. Okay, so let me, actually I'll keep that and I'll write it here. So there's a concrete example. And was it 1997? I don't remember exactly. Just 20 years ago. And I think it was December of 1997, by the way. Because he gave a seminar at CERN about it at about that time. Okay, so that's where this works. So the field theory is not generic garden variety Yang-Mills, but it's actually not that far away. Well, far away in some ways, but it has a lot of the structure we've described anyway. So n equals 4 supersymmetric Yang-Mills theory is what the gauge theory is. And over here, it's sort of equally bizarre. What you do is, well, the world sheet of the string, these psi's, you let them wander off not only in the directions transverse to the string, right? So in 4 space-time, it's codimension 3. There are 3 directions that could wander off there. You add extra dimensions. You add a 5th dimension. Actually, you add more than a 5th dimension. You add a 5th dimension, and then you add 5 more. So you add 6 dimensions to space-time. And you say that our theory is in this 4-dimensional subspace, and we live here, and that's all we can see. But the string world sheet can wander away into higher dimensions. And then when it wanders away into higher dimensions, it is just one of the perturbative string theories that you should be learning about in the other course. It is the type 2b superstring up there. And it's a type 2b superstring expanded near a particular background, which is 5-dimensional anti-de Sitter space in direct product with the 5-dimensional sphere. So the string model is a type 2b superstring. This 5 is down, and this one's on a particular background with some of the fields excited. It's not a vacuum solution in a sense of the 2b superstring. It has a Ramond-Ramond 4-form flux excited. And it's also not a flat background. It is this product. And this Ramon 4 form flux is emanating out through the 5 sphere. So the integral of d of the 4 form on a surface that links the 5 sphere gives you this n unit. And this is the n of the SUN in the gauge theory, or the UN. And then there's some mapping of the coupling constant. Actually, these spaces have constant curvature. They're both the sort of unique constant to negative curvature spaces of their dimension. On the solution of the string theory, the curvatures are equal, and the radius of curvature to the 4th power is equal to the Yang-Mills coupling constant times this parameter n. Okay, so this gives a concrete model where this actually works. Well, works is conjectured to work.
R to the 4th power is the radius.
The radius of R is the radius of the S5 and of the ADS5. The radius of curvature. So in ADS5, S5 it really is the radius. ADS5 it's, well, some analytic continuation. That's R. So R to the 4th power is identified this way. Yes, thank you. No, I just made a misprint. I forgot the alpha prime. Yeah. So of course the radius should have distance units. The alpha prime of string theory is distance squared. So it's like the fundamental string tension, and it appears squared in this formula. And we will have a lot more to say about this duality. Actually, these theories are thought to be exactly dual to each other. Exactly dual meaning they're the same theory. Right? They have the same quantum states, the same operators, the same correlation functions, the same everything. One-to-one mapping of everything onto everything. That's the strongest statement of the duality. It's also part of it that isn't really checked all that well. What is checked is certain limits of it. And those limits I will talk about. I don't know. I'm going to run out of time here. So I'm already going slower than I promised to go. But those limits I will talk about shortly. One of them is the so-called large n limit, which I've preserved down here because I'd like to discuss it a little bit, since just about everything one does here, in a technical sense, the things that one can do are in the large n limit. So I should introduce that carefully on the gauge theory side, just so that you know what it is all about. Okay, let me see if I've forgotten to say anything, and I can go on to talk about large n. Okay, so we will come back to this. In particular, we'll come back to how you do this computation in the string theory dual. Now, in n equals 4 super Yang-Mills theory, actually this is a conformal field theory. So the running coupling that I told you about from generic Yang-Mills actually doesn't happen there. Asymptotic freedom, confinement, and all those things are actually absent in the conformal field theory. That's a little bit surprising that that's where you found your string theory. Maybe that's what made it so hard to find. It actually applies in a place where you didn't really expect you needed a string theory dual. But in that case, there is a tool one can use to do the computations, and that is perturbation theory. So one could compute in weak coupling and compute the Wilson loop perturbatively there. It is a well-defined computation. And one can compute it this way And this computation turns out to be good in the strong coupling limit. To compute in string theory, of course, that's a tall order. I'm given a string theory, I'm supposed to calculate something. Well, calculating almost anything is a hard problem. It's only really tractable in some limit where the string theory is solvable. And just like field theories, that limit tends to be a semi-classical limit of some kind. And so where this problem is computable is in a semi-classical limit of the string theory, where this background is really classical gravitational fields, in a sense, and where the fluctuations of the string are greatly suppressed. And that limit turns out to be analogous to a strong coupling limit of the gauge theory. In fact, that limit is a small curvature limit, where the large radius of curvature limit, which is a small curvature limit in a sense, where r gets really big, it turns out to be strong coupling. So this side is computable when this Yang-Mills is, this side of the blackboard is computable when Yang-Mills is strong, this side when it's weak. That gives two complementary approaches to the problem, which compute strong coupling and weak coupling. And in fact, for Wilson loops, I'll show you how you can compute the whole thing, actually. Compute it at weak coupling, some perturbation theory to all orders, get some function of the coupling constant, extract the strong coupling, and compare the prediction. And that's sort of one somewhat non-trivial test of this idea. Okay, so this is where we'll go in future lectures. Let me try and finish this one by talking about the large N limit. So large N perturbation theory. What is the large N expansion due to 't Hooft? This, of course, you can look up in many review papers, so I've tried to give you something a little extra here. So let's come back to Yang-Mills theory and talk about large N. So large N is a rewriting of perturbation theory in something which looks like a stringy expansion. So we have to talk about perturbative Yang-Mills for a moment. So to do perturbation theory, I do have to fix the gauge. And let me put the coupling constant together with the gauge field. So instead of a factor in front of the whole Lagrangian, let me put it with the gauge field. Those of you who are familiar with this might think of it as a silly thing to do, because it's usually easier the other way around. But I would like to do a little more than one usually does, in that I would like to talk about Feynman diagrams that have external lines, and then it's actually easiest to do it that way. So here's what my Lagrangian looks like. Actually, I'll copy it from my notes to make sure I don't make mistakes. A gauge fixed Lagrangian in a relativistic gauge. Oops. No minus sign here, sorry. Put the minus sign here. So there's my matrix gauge field. I've taken apart the F mu nu because I've gauge fixed, so I no longer have to worry about gauge invariance, right? That's all been dealt with. I'll fix one of the common relativistic gauges, which is parameterized by this psi. So there's what the quadratic terms in F mu nu squared turn out to be. Then, of course, there are some Faddeev-Popov ghosts. And then there's some vertices. I'll write them in order, so minus I. And the Yang-Mills coupling constant isn't in front anymore. In fact, it's in front, now it's in front of the nonlinearity or non-quadratic terms in the action. Oops. For example, this one. So I haven't gone to components here. I'm still writing things as matrices. So C, for example, is a n by n matrix. It's no longer Hermitian, in the sense it's complex, and C bar is its complex conjugate. You could write it as the sum of a Hermitian and anti-Hermitian matrix if you like, to stick to Hermitian stuff. And then there are the usual Yang-Mills theory vertices. The cubic vertices, the ghost and the cubic one for the Yang-Mills field gluons go like G Yang-Mills, and then the quartic vertex which is two commutators of A with itself, goes with G Yang-Mills squared. Okay, and this is the action that you would use to start doing perturbation theory. So the Faddeev-Popov ghost came from gauge fixing, so did this. This is introduced in a sense to make the quadratic form and derivatives here invertible. And that's what you need for your gauge field propagator. You can deduce Feynman rules from here. I won't do that. I'll just take from them what features I need as I go along. So you get an expansion of, say, the Wilson loop computation or any other computation you would like. We fixed a gauge. We don't have to limit ourselves to gauge invariant operators. So we could calculate any correlation functions of the gauge field, say, that we like. They will depend on this parameter xi unless they're somehow assembled in the gauge invariant operators, but we're not really concerned about that at this point, just that this is a tool for doing computations. I would like to keep the notation where the fields are matrices. That leads to what's called the fat graph notation in the following way. So in the Feynman gauge, which is psi equals 1. It's not really crucial to be in the Feynman gauge. It's just a little bit less writing. The free field two-point function looks like this. Looks like this, and then it's basically times what would be the two-point function for a photon field if you were doing electrodynamics. And of course in here should be the e to the I k mu x minus y mu. The two-point function of the ghost field in the free field theory, so calculated in the limit as the coupling constant goes to 0. Also has these two delta functions, which are the only part of this that's really going to be important for us. And then again, the two-point function of a scalar field with a funny sign. I think it has the opposite sign here. It would be minus I if it were an actual scalar field. It's plus I because this is a ghost field. And again, the difference won't matter to us much, but has to be taken into account if you're going to do a real calculation of some kind, which we're not going to do. We're just going to estimate Feynman diagrams. So the essential part of these delta functions. These delta functions come from the indices here. And they're there because, well, we fixed the gauge. We no longer have local UN symmetry, but we still have global UN symmetry. Right? This action still has a global UN symmetry where you take a constant UN matrix and conjugate the A's and the C's with them. Right? That is a symmetry of the theory. And that symmetry leads to restrictions on the dependence of these two-point functions on these matrix indices. And for UN, that dependence has to look like this. In other words, it matches the first with the last and the second with the third. If this were SUN and not UN, this would look a little different. For SUN, this thing would be replaced by itself minus 1 over n times something with the indices permuted. So for SUN, there's a difference here. And this difference is a little bit complicating. Complicates the analysis. And I'm going to ignore the difference for now. The difference goes away as n goes to infinity. And so the leading order in of UN and SUN, the large n limit in the leading order, will be identical. But the next to leading order will have small differences. Already at order 1 over n, there are differences. And those differences are solvable to some extent. One can figure out where they go, but it is not that easy to do. It's technically involved, and I'm just going to ignore it here. So from here on, I'm working with this, which is UN. I should write that. Not SUN. Okay, this form of the propagator leads to a kind of a nice diagrammatic notation, which was actually invented by mathematicians a long time before particle physicists started doing this. There was actually a Canadian mathematician named Toot who used statistical models with matrix degrees of freedom to study things like map coloring problems, and this comes from the early 1960s. And so the thing that we call matrix models was actually studied by mathematicians a long time before physicists took over the subject, and a long time before 't Hooft. So some of this stuff comes from way back there, including the so-called fat graph notation. The gauge field propagator, which is this thing, when you usually draw a Feynman diagram, it's a squiggly line. Actually, it's usually a squigglier line than that. This squiggly line is normally used for the photon. The squiggly line for the gluon actually looks like this. That's in that notation where you use the Li Algebra basis. Here I want to use a different notation. Here I want to use the matrix element basis, these things. In that case, it's useful to use a double line notation. The lines are oriented and go in opposite directions. I never remember which is going which, but you should make a convention and stick with it. And the two sides you label by the matrix indices on the two sides. So one side has A and B, and the other has C and D. And you put the C and the D where the delta functions on this side tell you to put them. So D has to go on the line with A, and C has to go on the line with B. And then the orientation of the lines are such that you go from the first index of a matrix to the second index of a matrix by following the arrow on the line. And these will be the propagator components in Feynman diagrams. And then if you, and you can also do this for the ghost field, it's just the same. So the ghost field should also have some kind of a notation. And I'll practically never write a ghost, so I haven't even bothered in notes to invent a notation. But you could say, have a dotted line like that. And then it's the same A, D, B, C. The same idea for the ghost field is that the arrow should go from first to second. And then the ghost is also a complex field, so there's presumably more orientation to this thing than I've written there. There should be an overall orientation, which is first and which is second in a CC bar correlator, since it makes a difference. Okay, so you have this fat graph notation. Then you can also put the vertices write them as vertices for fat graphs. And that's simply following figuring out what the vertices are using the matrix components. And then through the vertices, one should follow double lines. So they're external lines, which will be these double line things. And then, for example, being a trace of a product of three matrices, the 3-point vertices will all have this structure. There's some things that are suppressed here, like derivatives of the fields that appear there, and so on. Also, there are several permutations of the same thing. But as these matrices, the indices of the matrices of the fields go on these external lines, the lines are always oriented so they're opposite to each other, like this. And so the orientation is consistent flowing through the diagram. So 3-point vertices will be like that. 4-point vertices will look like this. And again, the double lines are flowing through them like so. And then one makes Feynman diagrams by joining vertices like this with propagators like this. And so a generic Feynman diagram, well, looks like a usual Feynman diagram, but with fattened up lines. They sort of double line or fat graph notation. So let me draw a few examples. So let's say we're calculating vacuum energy. That's the easiest one. It has no external lines. And so just the leading thing is this vacuum diagram, which would, for a gluon, have looked like this, and there should be a ghost field one too, but now we fatten it up like this, and we have these lines going in opposite directions here, something like that. Okay, and then you notice what joining these lines up and summing over the indices does for you. Each time you do that, each time you make a closed loop out of these lines, and sum over all the indices, you simply sum over, in a sense, the color that's circulating around the loop. So each closed loop gives you a factor of n, the so-called index loop. So index loop and so this diagram goes like n squared. You can see by just counting the index loops. And so what this fat graph notation is for is just to figure out where the index loops are and what the factors of n are. And these you can think of as the group theory factors that come along with Feynman diagrams if you're more used to the other kind of perturbation theory. So it'll generate n's, and then what else will it generate? Well, 3-point vertices had a G-Yang-Mills in front of them, and 4-point vertices have a G-Yang-Mills squared in front of them. And given that, we're actually ready to count the powers of n in a given Feynman diagram. So let's say we have some Feynman diagram. We don't even have to write one down. We can just put one in our imagination. It has a bunch of internal lines. These are the propagators that I just erased here. It has a bunch of vertices. They're all connected together. The connections result in a certain number of index loops. So let's label in a sense, the general characteristics of a Feynman diagram. Let me call E the number of internal lines. V3 is the number of 3-point vertices. V4 is the number of 4-point vertices. I can see I'm going overtime here. Yeah, let me just finish the definition of these things, because There isn't really a better place to stop than that. Okay, what else? Well, the Feynman diagram will have index loops. Let me call the number of index loops f. Why the notation? Well, in a given Feynman diagram, it might look something like this in, say, non-fat graph notation. The internal lines are these things. Every line that connects two vertices are those things. There might be external lines. I guess I better define them. So let me call epsilon number of external lines. All of these things define the graph. In a sense, V3 plus V4 define the number of vertices, these things. Internal lines are these things, external lines are these. And then faces, index loops. When you fatten this to a fat graph, inside here will be some number of index loops like this. So this I would call an index loop. As an abstract graph, you can think of these as the following. The internal lines are what are called edges. The vertices are what are called vertices. And the index loops are what are called faces. And so you have a graph made out of three kinds of objects. Vertices, and then edges between faces, and then faces themselves. And as an abstract graph, we'll be able to discuss the topology of the graph. It has an Euler number, which is the number of edges minus faces plus vertices. Well, minus faces minus vertices, okay, something like that. And we'll be able to discuss it a little more. And I've run out of time here, but I will continue this discussion next time by starting from this point. So thank you.